Tom Overby here again. Welcome to the second part of our three-part slide set on power system transient stability analysis. At the end of last time, we had introduced the single machine infinite bus example in which we had a generator modeled with the classical model supplying power to an infinite bus through two parallel transmission lines, and then we had a fault occurring on the line side of the bottom transmission line, and we had assumed that this was a balanced three-phase fault, so it was a solid short to ground. Okay, what we had then was an equation for the electrical power out of the generator pre-fault. We had an equation for the electrical power out of the generator during the fault. Since it was a solid fault, in essence, on the terminal of the machine, we weren't able to get any power out during the fault. We cleared the fault by opening one of the transmission lines, so we had our post-fault curve here. Our initial operating point, the equilibrium point, was determined from the pre-fault conditions, and then we're going to see during this slide set that we solved the swing equation here to determine how delta changes with time. The first step in doing this is to determine the initial value for delta and the internal voltage magnitude for the classical model. This is known as back solving to get our initial values for the dynamic, or what we'll call the state variables. And this is found by using the pre-fault conditions, the power flow solution. For our single machine infinite bus example here, what this requires is that we know the initial power being supplied by the generator into the infinite bus. So let's put some numbers into this example. Let's assume it's a 60 Hertz generator, infinite bus voltage is 1 per unit, and we'll assume the generator is supplying 1 per unit power with a power factor of 0.95 lagging. For impedances, let's say the top line has an impedance of Z equals J 0.2, and for the bottom line it's J 0.3, all numbers on 100 MVA base, and we'll assume the classical model had an XD prime of 0.3. So to solve this, what we take is the fact that we know the initial power into the infinite bus, 1 per unit real power. We use the fact that the power factor is 0.95 lagging. That gives us its initial reactive power of 0.3286, recognizing that voltage times the conjugate of current is power. If we know the power, we know the voltage, take the conjugate. That gives us the current flowing out of the generator into the infinite bus. That current is flowing through an equivalent impedance, Z Thevenin here, in which it's just the internal reactance of the generator, 0.3 here, in series with the parallel combination of the impedance of the two transmission lines, and that gives us a Thevenin impedance of J 0.42. We can then just solve for the fact that the internal voltage here is just the infinite bus voltage plus the current times the impedance here, and that gives us the internal voltage expressed in rectangular coordinates. We convert that into polar coordinates, and that gives us an initial value for EA, magnitude of 1.213, and an initial value for delta, which we can express either in degrees or in radians. To verify this, we recognize that pre-fault P electrical needs to be equal to the specified 1 per unit. If we're supplying 1 per unit into the infinite bus, there's no resistance modeled here. So the electrical power out of the generator must equal 1, which is going into the infinite bus, which gives us our initial value for the mechanical power coming into the generator. Okay, the next step then is to solve the differential equations. To do this, what we're going to do is some numerical integration of the differential equations. Let's assume that we've got the problem in the form of x dot equals f of x, where we've got some initial conditions. Now right now we've got a second order differential equation, but we'll show how to convert that into two first order differential equations in just a second. If we've got our problem in this form, this is known as an initial value problem. Since we know the initial value of our state variables x, it's given at some time t naught, then what we want to do is determine the value of x sub t for future time. Now, we know from earlier electrical engineering classes that if this is a linear system, we can actually determine an analytical solution. But for problems such as transient stability, which we're going to see has a number of nonlinearities, an analytic solution is really not possible. So really the best we can do is to use numerical integration techniques. Okay, so just to give you two examples here. In the first example, let's just look at a very simple differential equation, x dot equals minus x, where we've got some initial value, x at time t equals 0 is some value x naught, and we know that this is just an exponential decay where x sub t is going to decay to 0 with the initial value e to the minus t. It's pretty easy to see that when you substitute in t equals 0 here, x sub t equals 0 is x naught, and then we have an exponential decay. The second example is, let's go back to the mass spring system where we had a mass suspended from a spring. We know that the force of gravity is pulling down, the spring's pulling up. We saw in the first slide set we can write the differential equations here. This is a second order set of equations of the form similar to the swing equations. What we can do is convert this into the set of two first order differential equations by letting x1 represent the position of the mass, and then x2 is equal to its velocity. So we've got that the change in the vertical position is just equal to its vertical velocity. And then x2 dot, which represents x double dot here, we just solved this equation for x double dot, which is x2 dot, and we can now write this in terms of x1 and x2 here. Okay, so we've taken a second order differential equation, used a variable substitution where x1 corresponds to x, x2 corresponds to x dot, hence x2 dot corresponds to x double dot, and we've got x1 for position and x2 for velocity. Okay, there are lots of different ways in which differential equations of this form can be solved numerically. Given the short intro that we're doing on transient stability, I thought it'd be good just to very briefly introduce the simplest of these methods, which is known as Euler's method. Euler's method is not a particularly good method to use in production grade software, but it does have the advantage that it's relatively easy to explain. So I'm going to go through it very quickly here. The key idea on Euler's method is we can take x dot equals some function f of x sub t, that's equal to the derivative of x with respect to time, and we approximate that as delta x over delta t. So then we can approximate the new value of x, be this a scalar or a vector function, at some time t plus delta t as being equal to the value of x at t plus delta t times the derivative of x evaluated at the current time. So delta t times f of x sub t. In general, with most numerical methods, you get a more accurate result if you use a smaller value of delta t. So delta t is known as the time step. Of course, the trade-off here is as you get a smaller delta t, that means you have to solve the set of equations more often, which adds to the computational complexity of the method. Okay, the algorithm for Euler's method is you pick some initial time, usually t initial is equal to 0. You know then your value of your state variables at that time. X at the initial time is equal to the specified value. We pick a time step, delta t, where that's going to be problem specific, what works and what doesn't work. And then we iterate while t is less than t end, we calculate x at the next time step is just equal to x sub t plus delta t times our function evaluated at the current value of x, and then we increment time. Okay, so to give a simple example here, let's again consider that exponential decay where we've got a scalar problem, x dot is equal to minus x. We know its initial value. Now in this case, we know the analytic solution, so we can take advantage of this to compare the accuracy we get with Euler's method with what we get from the accuracy between Euler's method and the actual solution when we use Euler's with different time steps. Okay, so let's, in this column here, here over on the first column we represent time. Second column here we give the actual value which we get from the analytic solution. Here we give the value of x that we would get if we used Euler's method with delta t equal to 0.1 second. Okay, we would start out with the initial value of 10, and then the value here at the next time step, t equals 0.1, is just 10 minus our delta t times our function evaluated at that time step. Our function is just minus x, so this is 10 plus minus 10 times 0.1, which gives us 9 here. We then repeat that for the next time, 0.2, we get 8.1, 0.3, 7.29. You can see this is just 9 minus now 0.1 times 9, and so on, and we're decaying down to 0. You can see that we're fairly close here, but we do have a little bit of error. Now if we have the time step, so t, or delta t is now equal to 0.05, we start out with 10. Now we evaluate the value of x sub t at t equals 0.05. In that case, it would be equal to 10 plus 0.05 times minus 10, which would give us 9.5. Then we do that again, and we get a little bit better accuracy here on our estimate of x sub t at the time t equals 0.1. Okay, now that one's relatively straightforward because it's just got a single variable. Now let's consider the second example of the earlier mass spring case. x1 represents the vertical position, x2 represents its velocity. Now we've got, I substituted in some relatively straightforward numbers such as m equal to 1. So we reduced it down to where x1 dot is equal to x2 and x2 dot is equal to minus x1. Okay, so let's assume an initial condition where we've got the mass at position 1 and it's at steady state, so it doesn't have any initial velocity. Again, we can use our analytic techniques to solve this since it's a linear set of equations, and we know that analytically x1 as a function of time is just going to be cosine of t. So it's just going to oscillate around. There's no damping in this example, so it'll continue to oscillate with going up and down with a value given by x1 sub t equal to cosine of t. So what we can do here is again compare the analytic with the numerical results. Okay, the way we solve it is let's pick a time step. In this case, I picked a rather large time step of delta t equal to 0.25. Then what we're doing is at each time step we're solving now two equations. x1 at the new value of t, 0.25, is equal to its initial value times delta t times, in this case, f1 of x evaluated at time t equals 0. So this term here just represents this here, x2, and in the second equation, it's just going to be minus x1. So here I've got x2, here I've got minus x1, and I get our value of x after the first time step is, surprisingly, our mass does not change position, but now it's got some velocity where it's starting to move upward. So you can see that intuitively it doesn't make sense that it would stay in the same position but get velocity going upward. Okay, that's one of the disadvantages with Euler's method, is it's not really that accurate. Okay, but let's continue on to the next time step. Now we've got x1 at the second time step, 0.5 seconds, value at the first time step, plus our delta t, x2 evaluated at 0.25, which we get right from here, so it's minus 0.25. That gives us that now our position has changed to 0.9375, so we're starting to move up, and we've got a new value for our x2. We've got x2 at 0.25, delta t here, and we've got a value here now of, let's see, this value right here. So we just substitute in there, and we get 1 again, so we're at minus 0.50. Okay, so if we continue to do this and we compare the actual, which is just the sinusoidal function, we're just oscillating back and forth. As t changes, we're always bounded between 1 and minus 1. What we find with Euler's method, though, is that initially we're getting some error, but in contrast to the earlier example, the exponential decay, that error does not die out. Rather, it tends to grow. So by 1 second, we're not too far off. But if you continue doing this, by 10 seconds, we're at minus 3. And by 100 seconds, we're at minus 151,000 for our position x1. Clearly, Euler's method is not working well with the time step of delta t. In fact, this is one of the disadvantages of Euler's method, is it can be what we call numerically unstable, so that even though the system itself is just oscillating back and forth, Euler's makes it look like it's going unstable. Okay, we can then compare Euler's for different values of delta t for what is x1 at time t equals 10 seconds. Actual is minus 0.8391. Here's what we got when we use 0.25. Clearly a bit of error there. If we drop the time step down to 0.1, we're getting a little bit closer. 0.01, closer still, 0.001, and we're not too far off here. So Euler's will give us relatively good results as long as we set delta t sufficiently small, where what is defined as small is problem specific. Okay, so now having that background, we can actually take our earlier problem, and here I'm going to do a complete solution on it, though I expanded it just slightly. Rather than putting the fault right at the terminal of the bottom transmission line, I've moved the fault so it's a third of the way from the left terminal to the right terminal line. We can represent that in a simulation by dividing the line and putting in a new bus here in which we've split the impedance of the line. So now we're going to put a solid fault at bus 3. And also to make the example a little bit more reasonable, I've modeled a step-up transformer for our generator, and I've assumed that the step-up transformer has an impedance of J0.1. So what we'll see is all that does is it's another impedance in series with the internal impedance for the generator. Now we're going to put in a value of H. Here we'll assume it to be 3 seconds. We'll initially start with 0 damping, and I picked a time step of 1/100th of a second. Okay, so just like we did in the earlier example, we determined the pre-fault conditions. Again, our generator is supplying 1 per unit power at a power factor of 0.95 lagging. So we get the same current that we had before. The impedance here is the same as before, except now we've got the impedance of the step-up transformer, so this changes just slightly. That alters our internal voltage slightly, and it alters our internal angle delta slightly. And again, we verify that pre-fault we've got PE sub delta is equal to 1, which is what we specified, and that determines the initial value for the mechanical power going into the generator. Okay, so we can then kind of sketch out the three systems that we're dealing with during the fault using the graph here over on the left. Here's the schematic of our system. We've got our internal voltage, delta, got XD prime in series with the J0.1 from the step-up transformer. We put our fault a third of the way down the line here. And what we see is that during the fault, if we're at our machine looking out into the network, it no longer looks like this voltage is solidly grounded. Rather, we've got a voltage divider here where we've got 2/3 of the impedance here, 1/3 here, our Thevenin infinite bus voltage. This voltage at this point during the fault looks like a third of per unit volt. So V Thevenin during the fault is 0.33. Then we look at what is the Thevenin equivalent impedance looking out into the network during the fault. We've got the 0.4 reactance here. Then we've got that in series with the parallel combination of 0.1, 0.2, and that gives us a reactance of 0.4 plus 0.66. And that gives us X Thevenin is this value right here. So we see that during the fault, our P electrical is not 0, rather it's 0.9152 sine of delta. Now what's interesting about this is while that fault is on, if we're continuing to supply 1 per unit real power into this generator, there's no way we can get 1 per unit real power out because this value, the maximum is going to be is 0.91. We again clear the fault by opening these two breakers right here, and then we go to our post-fault system, in which again our Thevenin voltage is 1 per unit, internal voltage magnitude stays fixed, and now we've got J0.4 in series with just this impedance, so our net X here is 0.6. So this is our post-fault system. Okay, so we've got pre-fault, faulted, and post-fault, and what we're going to determine from the numerical simulation is how long can this fault stay on and this generator stay in synchronism with the rest of the system, in this case represented by the infinite bus. Okay, so now we set up the equations that we want to integrate. Recall that M in the swing equation is H over pi Fs. We said that H was 3 per unit. We're operating at 60 hertz, so we've got M is equal to here 3 divided by pi over 60. This term right here is 1 over M. We initially have P mechanical set from the initial conditions. So P mechanical 1 stays fixed here. This is our fault on equation. And then we're going to initially assume that our damping is equal to 0. So the differential equations we're solving are x1 dot is equal to x2, and x2 dot is as given here. We use the power flow to give us the initial conditions. This is the initial value of delta, and in steady state, of course, delta dot is going to be equal to 0. Okay, we then solve this using Euler's method. Our initial value is given by the initial conditions here. With Euler's method here, we take the initial value x sub 0 plus the time step delta t, and we evaluate this. X2 is equal to 0, so this term right here will be 0. We substitute in x1 evaluated at time t equals 0 into this equation here, and we get 39.49. So this gives us our initial value for our value of x at the first time step. Angle stays constant, but it starts to get some delta dot here. Repeating the process for the second time step, and now we get the angle changing and we get the speed continuing to increase. So while the fault's on, what's going on is our generator is starting to accelerate, and it's getting a delta dot that is positive, and it's then causing delta to increase. Okay, if we simulate this out over 2 seconds, if we clear the fault after 0.1 seconds, we get the blue response here, and this would be a stable condition where this is showing how delta changes with time. If I clear the fault after 0.2 seconds, what happens is we get an initial larger rise in delta, but since we're clearing the fault, delta starts to decrease again, and we oscillate. It's a larger oscillation. Recall there's no damping in this system, so these oscillations do not decay with time. But again, we could say we're stable. If we delay the clearing until 0.345 seconds, it turns out that the system, actually the generator, loses synchronism and delta starts to increase, and that would be what we call the critical clearing time for this second. As long as this fault is cleared within about 0.34 seconds, the system will stay stable. Anything longer and our generator loses synchronism. So that's one of the problems that transient stability can tell us, is how fast do we have to clear these faults to keep the system in synchronism. Okay, while it's useful to do this by hand, except for the simplest systems, it really helps to have a computer program to do this. You can either write your own computer program, or for all but the simplest of systems, you're going to want to use some commercial package to do this type of transient stability analysis. A package that we originally developed here at University of Illinois for teaching power system analysis, it was originally developed back in the 1990s, is known as PowerWorld Simulator. This is a package that's still widely used for educational use. There's a free 42-bus educational version available with several example cases. If you go out to the website given right here, www.powerworld.com/Glover-Sarma-Overby, you'll be able to download the package and the demo cases. I'm going to show you an example of one of the demo cases here in just a second. There's also a quick start guide for using PowerWorld with transient stability that you can reference at the website given there. Okay, so what this next slide is going to show is the case that I just described to you, modeled in PowerWorld Simulator, where we're going to clear the fault at 0.34 seconds, but rather than starting the fault at time t equals 0, we're going to start the fault 1 second later, just so I can briefly explain the response of the system. So here I'm loading the case into PowerWorld Simulator. This shows the one-line diagram. We're going to fault the system at bus 3. What I'm doing is I'm calling up the transient stability add-on to PowerWorld, which models the fault. The fault is shown there down on the bottom. We're going to apply the fault at time t equals 1 and then clear it 0.34 seconds later. So what you're going to see here is a dynamic simulation where the graph at the top, I'm moving it out of the way here, shrinking it down and moving it somewhere on the screen where it's not quite as obvious. That shows the rotor angle on bus 4, and the bottom there is time. You can also see on right here, time is going forward, Time t equals 1, we apply the fault, the rotor angle starts to accelerate, we clear the fault, and then we have our system oscillating around here. The green arrows there are showing the power output of the generator, and that's oscillating around. The rotor's position here is indicated by the animation on the rotor angle there. This is showing numerically the angle. This is showing the speed in hertz. So you can see that we're oscillating around here. This 0.34 clearing is right at the margin of stability. So our angle here got pretty close to where we would have lost synchronism. And then we run the system out to 5 seconds, and that'll show us the total response of the system. Okay, but one of the nice things about solving this in a simulation package is you can easily change the fault clearing time for the system. Okay, and I encourage you to download the software. This is actually example 11.6 from the sample cases that come with the software, which are also the cases that are included in the Glover Sarma Overbeat Power System Analysis book. Okay, moving on to the next slide. The classical model is how we introduce transient stability analysis to students. And it used to be that the classical model was actually used in at least some utility grade transient stability studies. Over the last several years, the classical model is being phased out and it's no longer widely used in practice. So really we need to at least provide an introduction to more realistic generator machine models. And also what we'll find is if we want to introduce other device models such as the exciters and the governors, it helps to have a model that goes beyond the classical. So what I'm going to do in the next couple slides is just give a real brief introduction to what's known as the two-axis synchronous machine model. Okay, so this is a more realistic synchronous machine model, certainly not perfect as no model is. Okay, but what it requires is that we express the equations for the machine in a reference frame that rotates at the rotor speed. So the standard approach to do this is to transform our variables from the network reference frame to what's known as the DQ reference frame, in which we've got the major, the director D axis, is aligned with the rotor poles, and the quadrature axis, the Q axis, leads the direct axis by 90 degrees. So in essence, we're shifting by an angle delta here. When we do that, the machine voltage and current are transformed into the DQ reference frame using the rotor angle delta. So what we'll have is the terminal voltage of the generator in the network, or sometimes known as the power flow reference frame. We'll define that as V terminal as it's equal to its real value plus J times its imaginary value. Then we'll do a coordinate transformation by shifting by delta, where if we want to express the network equation values VR and VI in VD and VQ, we just multiply them by this 2 by 2 matrix here. And if we want to shift the DQ back into the network reference frame, we multiply by this transformation matrix right here. So numerically, it's a relatively straightforward transformation, but it does tend to confuse students when they initially see it. But I thought it'd be good to at least provide an initial introduction to this in this set of slides, and then we'll use it a little bit later on when we talk about exciter and governor models. Okay, once we've done this, we can use much more detailed models for our synchronous machine. There are numerous models that exist for synchronous machine modeling. Okay, the following is a relatively simple model in which we represent the field winding on the synchronous machine, and we have one damper winding on the machine. So we've got, rather than a single internal voltage We now have an internal voltage EQ on the quadrature axis, EQ prime actually, and we've got ED prime representing the direct axis. We use the terminal relationships to relate VQ plus RA IQ plus XD prime ID gives you EQ, and then or EQ prime. Then ED prime is given by this equation here, where this is the direct axis representation of the terminal voltage, quadrature axis representation of the terminal voltage, ID, IQ represent the terminal current. We then have two differential equations to represent the dynamics of the voltages, DEQ prime and DED prime here. Okay, the torque generated by the machine is given by this equation right here, which is just the torque supplied at the terminal of the machine plus the losses associated with the rotor here. Okay, and then we've got our P electrical is just equal to the electrical torque times the speed. And in initial, when you're learning about transient stability, it's quite common to assume that omega PU is pretty close to 1 per unit. So it's often assumed that omega per unit is exactly 1 per unit here. In a real transient stability program such as PowerWorld, this value is going to vary as you do the simulation. But we then solve the differential equations, and that requires that, again, we determine delta. This can be actually determined by noting that in steady state, the angle on the internal voltage E here, where you calculate E by this equation, VT plus J XQI, gives you delta. So that's one way to determine, it's actually a relatively straightforward way to determine your initial value for delta, which is what you need. Okay. So let's go through an example here. In this example, we're going to determine the initial conditions for the case that we did before with the classical generator replaced by the two-axis model. We'll again keep H equal to 3 per unit with the unit of seconds there, damping 0. Now damping is going to be less important because we've actually modeled a damper winding on the machine. XD 2.1, XQ 2, XD prime 0.3, XQ prime 0.5. All these are per unit using 100 MVA system base. Okay, we again use our initial conditions to determine the current out of the generator. That's the same as before. Here it is in rectangular coordinates. Here it is in polar coordinates. As before, we calculate X Thevenin here, except now we're just going to calculate X Thevenin to the terminal of the machine. So this is just the parallel combination of the two transmission lines with the step-up transformer. That allows us to calculate the terminal voltage in its polar format, or the VD, the real and the imaginary part here. The next step then is we go ahead, we calculate delta using the equation which I just gave you. That gives us our initial magnitude of E here, and we use that to determine delta, which is 52.1 degrees. We can then use the equations that we derived previously to relate the VR and VI and the IR and II into the DQ reference frame, and that's what we've done with these two transformations here. Okay, then the next step is we need to determine the initial values for our differential equations. We're going to have an initial value for EQ prime. We're going to have an initial value for ED prime. We get that just by solving the differential equations for the fact that in steady state the derivative is going to be equal to 0. So if we go back to these equations here, what we get is we solve this one here by setting this term equal to 0, and we solve this one here by setting this term equal to 0, and that will allow us to solve for EQ prime, ED prime, and then we calculate the field voltage here. Okay, and that's what I've done right here. The transient stability solution is then again solved numerically by integrating the differential equations. Now we've added to our swing equation, we've added 2 more differential equations. What we're going to find in the next slide set is this field voltage is going to be what the exciter controls. So in the initial simulation, we'll assume the field voltage stays constant, and then in part 3, we'll actually introduce an exciter voltage that changes the field voltage. Okay, the PowerWorld solution of the 2-axis model can be, I debated whether to put the full solution in here, but I wanted to keep the slide set to a reasonable size, so I didn't put in a detailed solution here. But this is actually example, I believe it's 1110 in the cases that you can download. If you look at the rotor angle here, this is for a clearing time of 0.1 seconds. We're stable here, but what's different between this model and the classical model is now we've got a damped response where the rotor angle is decreasing with time, and that's because with the 2-axis model we were able to include a damper winding with the synchronous machine. So I encourage you to download this example and run through it. What we'll pick up with this example on the 3rd slide set is adding in models for exciters and governors, and then talking a little bit more about how we model the network power balance equations.